Lecture 21 covers section 6.7. At the end of today's lecture, you should be able to use the offsets model, the finite gain model, and both the offsets model and finite gain model to model the practical behavior of an operational amplifier. We will also talk about CMRR, or the common mode rejection ratio, applied to the finite gain model to increase the fidelity of our modeling of operational amplifiers. To begin, thus far, we have ignored a lot of non-ideal parameters of our op-amps. Firstly, we have ignored our input current. That is, we've neglected a non-zero bias current. We've also assumed the voltage at our inverting and non-inverting terminals is one and the same. Thus, we have ignored a non-zero input offset voltage. We have not talked about the resistance of our op-amp, such that we assumed it was infinite. And lastly, we didn't talk about limitations on the gain of our op-amp. The offsets model and finite gain model will address these issues, but we have to keep in mind, as we increase the fidelity of our model, is it worth the computational cost? Now, the offsets model accounts for non-zero bias currents. That is, if we look at the schematic on the left, where we would have I1 entering our inverting terminal and I2 entering our non-inverting terminal, we can place two current sources, IB1 and IB2, which are known as our bias currents. Additionally, our offsets model takes into account our non-zero input offset voltage, VOS. VOS is existing at our non-inverting input terminal. Thus, the equations of our operational amplifier becomes I1 is equal to IB1, and this is no longer a zero value. I2 is equal to IB2, which is also no longer a zero value. And the difference between our voltage potentials at our inverting and non-inverting terminals is equal to VOS, which is also a non-zero value. This model, however, does not account for a finite input resistance or a finite output voltage. The finite gain model will take those into account. Now, we have a term, the input offset current, which is given as the difference of our bias currents. We note that IB1 and IB2 do not have to be equal, they can differ, and this is designated as IOS. Now, what's unique about this model, in that it captures the practical behavior of operational amplifiers, is that our input offset bias currents are typically pretty small, on the order of tens of picoamps to tens of nanoamps. And our offset voltage is on the order of tens of nanovolts to tens of millivolts, also small values.